I want to start today with a really big, slightly intimidating idea.
Okay.
It connects Isaac Newton to basically everything we see around us. It's this claim that the fundamental laws of the universe, the actual source code of reality, aren't written in words. They're written in the language of differential equations.
It's a beautiful way to put it. And it's not just poetry either.
Yeah.
I mean, ever since Newton, physicists and mathematicians, people like Stephen Strogatz, have realized that if you want to talk to nature, you have to speak this specific language.
Right.
But the minute I say differential equations, half the people listening are probably flashing back to a calculus exam they barely did.
Oh, absolutely. They're reaching for the stop button right now.
Exactly.
Which is exactly why we are doing this deep dive, because I don't want to solve for x today. I barely remember how to solve for x, to be honest.
Same here sometimes.
I just want to know why this matters. Because the premise of the sources we're exploring today is that this math isn't just about crunching numbers. It's a completely different way of viewing how the world works. It's a shift from seeing things as static stuff to seeing things as change.
That is the absolute P right there, change. The whole reason this specific type of math exists, the reason Newton had to invent it in the first place, is that it is almost always easier to describe how something changes than it is to describe its absolute state at any given moment.
Okay, that sounds profound, but let's ground it for a second. Easier to describe change. Give me a real-world example where that's actually true.
Okay, take a population. Let's say the population of a specific city. If I ask you to explain exactly why the population is 1,402,000 people right now, today.
That's remarkably difficult.
It's impossible. You'd need the entire history of the city, every migration, every war, every economic boom.
Right. It's a massive data dump.
Exactly. But if I asked you to describe how the population is changing, that's simple.
How?
It's just the birth rate minus the death rate, plus whatever migration's happening. You can write a very simple rule, a differential equation, actually, that describes the rate of change perfectly, even if describing the current exact number is a mess.
So the rule is simple, even if the reality is complex.
Precisely. And in physics, this is the foundation of everything. Newton's laws don't tell us where a planet is. There is no rule that says Mars must be at coordinates XYZ at 2 p.m.
Wait, really? Because I assume that's exactly what physics did.
No, not at all. Newton gave us a rule about force. Force determines acceleration. And what is acceleration?
Getting faster or slower.
Right. It's a statement about how velocity changes. And velocity is a statement about how position changes.
Yeah.
The laws of the universe are fundamentally about rates of change. We have to work backward to figure out where things actually are.
Okay, so before we get into the heavy stuff, because I know we're going to talk about chaos theory later and why we can't predict the future, we need to sort out the toolkit. We've got these differential equations, but there are flavors, right?
Two main flavors. And the difference basically tells you how much of a headache you're about to have. You have ODEs, which are ordinary differential equations, and PDEs, partial differential equations.
I'm guessing ordinary is the one we want to stick with today.
Oh, absolutely. Ordinary differential equations usually involve functions with a single input. We typically think of this input as time.
Okay.
So imagine you're watching a movie of a specific object, a pendulum swinging, a planet orbiting, a ball falling. You have a finite set of numbers that change as the clock ticks.
Got it. And the partial ones.
That's the deep end. That's when you have multiple inputs. Imagine describing how heat spreads through a solid block of metal.
So it's not just about time.
Right. The temperature isn't just changing over time, it's changing differently depending on where you are in the block. So you have time and space involved.
Oh.
Or describing the flow of a river where every single drop of water has its own velocity.
Yeah, that sounds like a nightmare.
It is incredibly complex. So let's stay in the ordinary world, the physics playground.
Good plan. Let's start with a classic high school physics example. I throw a ball in the air.
The perfect warm-up.
So gravity pulls it down. We all know that. 9.8 meters per second squared. But you're saying that number of 9.8 isn't just a number. It's a clue.
It's the first breadcrumb in a detective story. Because that 9.8 tells you the acceleration. That is the rate at which your speed is changing. If you know gravity is constant, you can figure out exactly what the velocity is doing every single second.
Okay, but here's where I get stuck on the detective part. If I know the acceleration, do I automatically know where the ball is?
No. And this is the subtle part of solving a differential equation. It's called integration. Think about it like this. If I tell you I am currently driving at 60 miles per hour, do you know where I am?
No. You could be on the highway, you could be on a back road in another state. I have no idea where you started.
Exactly. You know my rate of change, my velocity, but you don't know my state, my position, unless you have one more piece of info, my starting point. We call these initial conditions. Solving a differential equation is the process of working backward from the rate of change, the acceleration, to find the velocity, and then working backward again to find the position.
You're rebuilding the history of the object based on how it likes to move.
That's a brilliant way to put it. Yes.
Yeah.
For a falling ball, it's easy. Gravity is constant. The math is clean. You can write a formula on a napkin that tells you exactly where the ball will be in 10 seconds.
But the universe isn't usually that nice, is it?
Rarely.
Which brings us to the pendulum. And I have to say, looking into the sources for this deep dive, I felt a little betrayed.
Betrayed?
Yeah, because I distinctly remember sitting in physics class learning the formula for a pendulum swing. T equals 2 pi times the square root of length over gravity. Something like that. It was neat, it was tidy. And now you're telling me that formula is basically a lie?
Well, lie is a harsh word, but yes, it's a fabrication. It's what physicists call the small angle approximation.
Okay, unpack that. Why did my teacher lie to me?
They lied because the truth is mathematically horrifying.
Yeah.
Here's the reality. When a pendulum swings, gravity pulls it straight down. Right. But the pendulum is on a rope. It has to move in an arc. So the force that actually pulls it along that arc depends on the angle. Specifically, it depends on the sine of the angle. Sine theta.
Okay, I remember sine from trig class. Curves, waves. That actually seems appropriate for a pendulum.
It seems appropriate, but mathematically, it's a disaster to solve. In high school physics, we just assume you're only swinging the pendulum a tiny bit.
Yeah.
Like barely moving it.
Okay.
Because when the angle theta is tiny, the number for sine theta is almost exactly the same as the number for theta itself.
So they just swap them?
They swap them out. They replace the complicated sine function with just the simple angle. That turns the equation into something linear and easy to solve. That's where your nice napkin formula comes from.
But what if I'm on a playground swing and I'm really pumping my legs? I'm going high. That angle isn't small anymore.
Exactly. Once you swing high, that approximation breaks down completely. The lie is exposed. The force is no longer proportional to the angle. It's proportional to the sine of the angle. This makes the equation nonlinear.
What does that actually mean for the person on the swing, though?
It means the period, the time it takes to swing back and forth actually changes depending on how high you go. A big swing takes longer than a small swing. The tick-tock of a grandfather clock is only constant if the swing stays tiny.
Wow.
If you really push it, the rhythm breaks. And solving that equation, the real one, with a pen and paper, it's basically impossible.
Wait, impossible? It's a pendulum. It's a rock on a string. How can we not have a perfect formula for it?
We just can't write a clean function for it. It doesn't exist.
Yeah.
And that's just a pure, frictionless pendulum. In the real world, you have air resistance.
Friction.
Right. Dampening. Now you have a force fighting the motion, and it depends on how fast you're going. So our equation has acceleration, the sine of the angle, and a velocity term for friction. Yeah. This is a dampened, nonlinear pendulum. It is a beast.
So if we can't solve it analytically, if we can't write down x equals whatever, do we just give up?
No, we change the game completely. This is the moment where modern math pivots from calculating exact answers to visualizing behaviors. We stop looking for a formula and we start building a map.
A map.
Yes. We call it phase space.
Okay, phase space. I really want to get this right because it feels abstract. We're used to graphing things where the bottom axis is time, right? Like position over time.
Forget time. In phase space, time effectively disappears from the axis. Instead, we want to graph the entire state of the pendulum. What two things do you need to know to fully describe what the pendulum is doing at this exact instant?
Well, I need to know where it is. So the angle.
Good.
And I need to know how fast it's moving. The angular velocity.
Perfect. Those are your two axes. Angle on the bottom, velocity on the side. Every single point on this 2D landscape represents a possible reality for that pendulum.
So a point at the very center. Zero. That means zero angle, zero velocity.
The pendulum is hanging dead still, pointing straight down.
And a point way out to the right with high velocity means it's swinging up high and moving really fast.
Exactly. Now imagine you pull the pendulum back and let go. On our map, that's a point starting on the angle axis with zero velocity. As time moves forward, the pendulum swings. The angle gets smaller, the velocity gets higher, the point on the map starts to move.
It draws a trail.
It draws a trajectory.
Right.
If there were no friction, it would just draw a perfect circle round and round forever. But we have friction. We have dampening. The pendulum loses energy.
So it doesn't swing as high the next time, it slows down.
Right. So on our phase space map, that point spirals inward. It goes round and round, but every loop brings it closer to the center. It's like watching water circle a drain.
And the drain is the point 0, 0.
Yes. We call that an attractor. The system wants to go there. Eventually, the pendulum will stop. The geometry of that spiral tells us everything we need to know about the pendulum's future, even if we can't write down a simple formula for it.
I really like that image. We aren't solving for a number. We're watching a point flow across a terrain. It's like the differential equation isn't a rule book anymore, it's a landscape.
That's a beautiful analogy. Think of the differential equation as a vector field. Imagine that 2D map is covered in little arrows, like a weather map showing wind direction.
Okay, I'm visualizing that. Arrows everywhere.
Wherever you drop your point on that map, the arrow right underneath it tells it where to go next. Move a little left and speed up, then it hits the next arrow. Move a little more left, slow down. The equation generates the arrows. The behavior of the pendulum is just the point following the flow.
So we've gone from order, the falling ball, to complexity with the dampened pendulum. But the flow is still predictable, right? The spiral always goes to the center eventually.
In the pendulum case, yes. It's complex, but it's well behaved. But this visual approach also reveals where prediction breaks down completely.
But before we get to the breakdown, there's a really fun detour here in the source material. Because these flows and spirals don't just apply to physics, Stephen Strogatz actually used this exact same math to model something completely different.
Romance.
Yes, love affairs, which sounds like a joke, but he actually wrote out the differential equations for it.
It's a fantastic way to understand coupled systems. In a pendulum, position and velocity are linked. In a relationship, my affection and your affection are linked. They feed off each other.
So let's build the model. We have a graph. My feelings are on the x-axis, your feelings are on the y-axis.
Strogatz describes a Romeo and Juliet dynamic. Let's say Romeo is a chaser. His affection grows when Juliet is distant, but Juliet is a runner. Her affection drops when Romeo gets too close.
Oh, I have been in this relationship. It is not fun.
It's not fun to live through, but it's mathematically fascinating. Because think about the arrows on that map. If Romeo chases, Juliet pulls back. That makes Romeo chase harder. But if Romeo pulls back, Juliet gets interested.
It's a circle.
It is exactly a frictionless pendulum. In phase space, the relationship just cycles round and round. Passion, indifference, frustration, hope. It never settles. It's a closed loop.
But wait, we talked about dampening with the pendulum. Friction. What does friction look like in a human relationship?
Caution. Fear of vulnerability. Suppose Juliet doesn't just react to Romeo, but she also has a dampening term on her own feelings. She stops herself from getting too excited. She pumps the brakes.
So what happens to the trajectory on our map?
Just like the pendulum, it spirals. The highs get lower, the lows get less dramatic. The relationship circles the drain until it hits the attractor at 0. 0.
Mutual ambivalence.
A boring, dead-end breakup. The math predicts it perfectly.
It's wild that the exact same geometric shape, that inward spiral, describes a swinging rock and a dying romance. It really drives home the point that this is a language of change, regardless of what is actually changing.
Exactly. But now we have to scale things up. We have to break the universe.
Right. We promise chaos. So we've done one object, the falling ball. We've done a constrained object, the pendulum. What happens when we add more pieces to the puzzle?
The three-body problem.
This is the famous one. We want to predict the motion of 3 planets orbiting each other in space.
It sounds like it should be easy. We know Newton's laws perfectly. We know the mass, the gravity, the starting positions. But when you move from 2 bodies to 3, the complexity just explodes.
Let's map it in phase space then. For the pendulum, we needed a 2D map. How big is the map for 3 planets?
Well, you have 3 planets. Each one has a position in 3D space, X, Y, and Z. And each one has momentum in 3D space. That's 6 numbers per planet.
So 3 planets times 6 numbers 18 dimensions.
Correct. The state of that solar system is a single point meandering through an 18-dimensional landscape.
I can't even begin to visualize that.
Nobody can. But the math is the same. The point follows the arrows. However, in this 18-dimensional space, the arrows do something terrifying. They diverge.
This is the sensitivity to initial conditions.
Yes. Chaos. Imagine you start your solar system at a specific point. You let the clock run, and the planets dance around each other. Now imagine you go back to the exact same start, but you move one planet by a nanometer, a billionth of an inch.
Effectively the exact same starting point.
You would think so. In a non-chaotic system like the pendulum, the result would be almost identical. But in the three-body problem, that tiny difference grows. The two realities start to drift apart, slowly at first, but then exponentially. After 1,000,000 years in one version, the system is totally stable. In the other version, a planet has been flung out of the solar system entirely.
And this is the butterfly effect.
That's the pop culture term for it, yes. But mathematically, it's about an information horizon. It means that no matter how precise our measurements are, we can never be precise enough. There's always a tiny error. And in a chaotic system, the error eats the prediction.
That feels really cruel. We have the source code of the universe, these differential equations, but we can't actually run the program to see the future.
It is a profound limitation. We can know the laws, but not the outcome.
But, going through the materials for this deep dive, there was a different perspective on this. It argued that while chaos theory is cruel, it's also kind of reassuring.
I strongly agree with that. Think about what we're really saying here. We're saying that the messiness of the world, the unpredictability of the weather, the stock market, human behavior, that isn't just noise. It's not just random garbage happening because the world is broken.
It's a feature, not a bug.
Exactly. The chaos is built into the math itself. The structure of that 18-dimensional phase space is inherently chaotic. It's supposed to be that way. It means the immense complexity of our lives is actually part of a structured geometric reality.
James Gleick, who wrote the foundational book on chaos called Phase Space, one of the most powerful inventions of modern science. And after walking through all this, I think I finally get it. It lets us see the shape of the unpredictable.
It lets us see the flow. And that is what I really hope you take away from this. We are so conditioned to think of math as answer equals 42. But differential equations teach us that the answer isn't a number. The answer is a trajectory.
So, here is a final provocative thought for you to chew on today. We spend a lot of time in our lives trying to solve for X. We try to figure out exactly where we should be in 5 years, or exactly what the perfect decision is to get a very specific result. But maybe, just like with the pendulum or the 3 planets, we can't find that exact formula.
Right. You can't solve the equation of your life analytically.
But you can look at the vector field. You can look at the immediate arrows around you. Where is the flow taking you right now? Are you spiraling toward an attractor you actually like? Or are you stuck in a Romeo and Juliet loop?
You might not be able to predict the chaos, but you can definitely map the flow.
And sometimes seeing the flow is better than knowing the answer. That's it for this deep dive into the language of the universe.
Keep looking at the big picture.
We'll see you next time.